Hi everyone, and thank you for joining me tonight. This is the Electrical Engineering 2310 exam review number one. This is for digital systems. Glad everyone can join me. This is going to be my first ever uh, virtual uh, exam review, so bear with me if there's some technical difficulties and whatnot. Let me go over a brief overview about how everything's going to work tonight. Also, if you guys can hear me, go ahead and send, if you can send a message in the chat just to make sure that I know everything is working correctly. So this is the agenda I have ready for the night. Microphone issues. I think I changed something. Do you guys hear any echoes now? All right, echoes are gone. Okay, that's great. Yeah, I think I had a setting wrong. All right, gonna continue. All right, so this is what I have set up for tonight. First thing I'm gonna go over is the review of binary systems. So what I'll be talking about is conversion between binary to decimal, some simple additions, how we use 2's complement to represent negative numbers, and subtraction. So how can we actually subtract two binary numbers using 2's complement? I'm then going to move on to some more fundamental logic topics. So I'm going to reveal our basic gates and or not, NAND, NOR, XOR, and XNOR, and their truth table and symbols. I'm going to review our basic Boolean identities. DeMorgans Law is a very important one that I'll be going over. How we expand Boolean equations into canonical form, so fully expanded SOP sum of products form, and I'll go over a little bit very briefly POS or product of sums. Simplifying Boolean equations just using some fundamental Boolean algebra, K-maps, and I'll be going over truth tables. I'll have an example with some CMOS logic, so given a circuit with some PMOS and NMOS transistors, find the output with a given stimuli, and then write that output function into a Boolean equation. Conversions, so NAND and NOR logic, you can use NAND or NOR logic to convert any Boolean expression to using just those gates. So I'll show how you convert any expression to NAND or NOR logic using one or two clever tricks in DeMorgans Law. Again, I'll be going over max terms and min terms and what those mean to Boolean equations. And given like a K-map or some kind of circuit diagram, how we write a Boolean equation for those. K-maps, I'll be doing a few examples of those. And I'll briefly go over muxes, decoders, adder subtractors, and I think you guys also did like a priority encoder in class, if I'm correct. And we have about 3 hours. I don't know if it'll take that long, but when I get through everything I want to go through, if there's any time, I'll maybe open the chat up to questions. And anytime during this presentation, I'm looking at the chat on another computer. If you guys have any questions, if you guys have any questions, go ahead and say those in chat, and I'll be sure to try to look back and forth periodically. I'm going to pause real quick and see if anyone has any questions before I begin. Okay, I'm not seeing any questions, and note in mind there's about a 10-second delay between me and you guys, so all right, we'll get started here. All right, so the first thing I want to go over is binary operations. See if my camera's working right or not. There we go. All right, so binary numbers. So how we operate with binary numbers. So we need to know how to go from decimal numbers to binary numbers. So I'm going to start out with our first kind of example here. So I want to add the numbers 64 and 41 together. So how do I do that? So there are several ways of converting decimal numbers into binary. Some people use this like law of successive divisions, where you keep on dividing by powers of 2 until you get somewhere. I like to just think about, so like I want to convert 64 into a binary number. So what I think about is what's the biggest power of 2 that I can fit into 64. And this is where it's good to memorize all your powers of 2. Well, I know off the top of my head, well, 2 to the power 6 is exactly 64. So what I'm going to do is I have a binary number that I'm going to write, and so I'm going to count. So this would be like the zeros place, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and I know that 64 is 2 to the 6, so I'm going to put 1 here and zeros everywhere else. So this is how you write 64 in binary. All right, so maybe let's go to something not as simple. So 41. So I'm going to think to myself, hey, what's the biggest number that's a power of 2 that I can fit in 41? Well, 2 to the 6 was 64. That's not going to work. 64 is bigger than 41. So then I'm going to think, oh, what's the next one? Well, 2 to the 5 is 32. Does 32 fit into 41? Yes, it does. So I'm going to go to 2 to the 5th, right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 4, 2 to the 5. And I'm going to put a 1 there, right? So now I have 32, which means I have 9 left. So this was 2 to the 5th. This is 2 to the 4th. Well, 2 to the 4th is 16. Can I fit 16 in the remainder I have? No, I can't. All right, so this is 2 to the 3rd, which is 8. Can I fit 8 into my remainder? Yes, I can, right? Let's put a 1 there. So now I'm left with 1. So this is 4. I can't fit 4 in there. Can't fit 2 in there, but I can fit 1. And so this is how I come up with my binary to decimal conversion. So this is the binary representation 41. Now, I don't want you to get confused right now. So later, I'm going to talk about 2's complement. And 2's complement is a signed number system. Right now, I'm just talking about purely unsigned numbers. This is very basic binary. All right, so now I've converted my numbers. Now I can add them, right, into binary. So what I'm going to do here is I'm going to write down my 2 numbers. So I'm going to do 64 plus 41. Add, and be sure when you're writing these, you like align them correctly. Right, and I'm just going to go down and add these. So 0 plus 1 is 1. 0 plus 0 is 0. This is 0 again. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. And there's like a leading 0 right here, right? So 0 plus 1, or 0 plus 1 is 1. So this is my result right here. So yes, I have my result in binary. So let's go the other way around here. This is an unsigned binary number. Let's convert it to decimal. So, right, so I see there's a 1 in this bit right here, and this is 2 to the 6 right here, right? So, right, 2 to the 6 is 64. This bit is also set to 1, and that's 2 to the 5th, which is 32. 16 isn't set, but 8 is set. Then I have 1. So, right, I'm going to add all these numbers together. This is 15. Here's the 1. 105. So this binary number and this decimal number both mean the same thing. They mean 105. And that makes sense, right? Because we were doing 64 plus 41. And obviously 64 plus 41 is equal to 105. So this is a quick example showing binary math. So now I'm going to move on to something a little bit more complicated. So we're going to work with 2's complement now. And if you guys have any questions, please let me know in the chat. I'm still looking at that. So 2's complement now. Now what I just did, I was working purely with unsigned numbers. But as you know, I want to have negative numbers in my number system. So that's why we have 2's complement. So right now I'm going to be working exclusively with an 8-bit number system. So every number that I write down, I'm going to represent with 8 bits, no more, no less. So let's go ahead and just start out with this example. I'm going to subtract 31 from 20. It's going to be my example here. So I see someone asked, can you do the conversion from binary again? I'll do another binary conversion here. So the first thing we want to do, so what's this operation going to look like? I'm subtracting 31 from 20. Well, in plain, regular math, I want to do 20 minus 31, right? Which is the same as 20 plus negative 31, right? So I can still do my binary addition, but I need to find out how I represent this negative 31. So this 20 is just a simple conversion, right? This isn't negative. We're going to write it the same way we do as normal. So what I'm going to do is, I'm going to do my little process again. I'm going to think of the highest power of 2 that can fit into 20. Well, 2 to the 4th is 16. Can 16 fit into 20? Yes, right? So I'm going to have, this is 2 to the 16th. If I put another 8 in there, right, I'm going to go over, I'm going to hit 24, so I'm going to put 0 there. To the second, 4, well, 16 plus 4 is 20. So this is going to be 20, right? Yes, this is 20. So this is 20 in decimal. Right, no surprises so far. And so when we work with 2's complement number, the leading zeros will matter in some cases. So since I said we're working with 8 bits, I'm going to go ahead and pad this up to 8 bits, right? So these bits in the front here are 0. Yeah, that's right. This is binary. All right, so that was easy. All right, here's the harder part. How do I get negative 31? So the process is kind of similar. First, I'm going to write 31 in binary, how we've been doing this entire time. So I'm going to do my same process. What's the highest power? Can't fit 32 in there, but I can fit 16, right? So 16, right? Can I fit another 8 in there? That'll add to 24, so yes, I can fit another there. So we're up to 24. Can I fit 4 in there? Yes, I can. Up to 28 now. Can I fit 2 in there? Yep, up to 30. 31, right? So this is, and then I'm going to pad it up, right? So I'm going to add these zeros until I have my 8 bits. So this is 31 in binary. So I'm going to convert this to a 2's complement number. So what I do is I invert all the bits. So if a bit here was 0, I'm going to change it to a 1. So I'm inverting all my bits. All these 1s are going to turn into zeros. So I've inverted my bits. So I'm going to invert, and then I'm going to add 1. So I'm going to add 1 to this number. 1, 1, 1. 0, 0, 0, 0, 1. I just did a simple binary addition. So this is the representation of negative 31 in 2's complement. So let me explain a little bit about 2's complement number. So this is an 8-bit 2's complement representation of negative 31. And a special thing about 2's complement is you see this bit right here? This tells you what the sign of the number is. So if I have a 1 here, that means my number is negative. And 0, if I have a 0 in the most significant bit right here, that means I have a positive number. Okay, so let's continue with this example. So I've got this, so I know what 20 and negative 31 are in my number system. So I'm just going to add them together. So I have, this was 20. And then I'm going to add this number we just came up with here, this negative 31 and 2's complement. I'm going to add them up. Right? So I'm just adding these. 0 plus 1 is 1, 0, 1, 0, 1, 1, 1, 1. So this is the result I get. So this is the result of my computation here. So right, the first thing I want to do is now I want to convert this to decimals to check myself. So now I want to look at this sign bit. If this sign bit is 0, this most significant sign bit is 0, then all I have to do is convert this number back to decimal, and I don't have to do anything else to it. It's just that number that I come up with. But this is the case to where the sign bit is 1. This means this is a negative number. So how do I figure out what the original number is? I need to do 2's complement again to this number. So what I want to do is I'm going to invert all the bits again, right? So all the 1's turn into 0's, and all the 0's turn into 1's. I want to add 1 to it, right? So this is my new number. And I'm going to figure out what number this is. So since I knew this was originally a negative number, right? I'm going to make sure to put my negative sign right here where I write my decimal number. And so this number is 8, right? This is 2 to the 3rd plus 2 plus 1. So this number in decimal is negative 11. That makes sense, right? Because we said I want to subtract 31 from 20, and 20 minus 31 is negative 11. So that's how we use 2's complement. If my result from this calculation didn't have this 1 right here at a 0, all I would have to do is just convert this number back into decimal. I wouldn't have to put any negative signs or do 2's complement. But if you end up having a negative result, you have to do 2's complement to it again to figure out, what your number is going to be, what this magnitude is going to be, and then make sure to add your negative if you end up with a negative answer. I'm going to pause here real quick, see if we have any questions. If not, I'll go on to start out with some Boolean algebra. All right, I don't see any questions, so I'm going to move on to some Boolean algebra here. Let me look at our agenda, see where we're at. All right, so we have the basic logic gates here. So we have an AND gate right here, and an AND gate looks like this, and this is the truth table. Just to go over truth tables real quick. So with the truth table, you have your inputs here on the left side, and your outputs here. You have your inputs here and your outputs here. So we have some gate here, and it has inputs A and B. You feed them through this gate, and we get this output A, B, right? And so an AND gate, you need to know all these truth tables and how the AND works and the ORs and all that good stuff. So, right, we have in the truth table, we see that the output is only 1 if both the inputs are 1, right? So if any of the inputs are 0, you're going to get 0 for the output. But if both inputs are 1, you're going to get 1 for the output. Moving on, we have the OR gate. It looks like this. It's like the AND gate, but it's kind of had a pointed nose and curved back right here. We see when we look at its truth table, if one of the inputs are 1, it doesn't matter if it's A or B. If just one input is 1, then that's going to turn the entire output to be to be 1. So if A or B is equal to 1, it's going to be 1. NOT gate. This is referred to as the inverter a lot also. Whatever goes in, you get the inversion of it. So if you have 1 that goes in, you're going to get 0 out. And a little bit later, I'm going to show you how you can make inverters out of NAND gates and NOR gates. This is what this is talking about right here. The NAND gate. We're going to be dealing a lot with those because with NAND gates and NOR gates, you can make any Boolean expression. You can form AND gates, OR gates, inverters, all that good stuff. So all a NAND gate is, it's like the AND gate, and it has an inverter on it. And so let's go back to this AND gate truth table. You see that truth table 0, 0, 0, 1. It's just the inverse of that. It's 1, 1, 1, 0. So with the AND gate, as long as one of the inputs are 0, you're going to get a 1 for your output. NOR gate, it's like the OR gate, but inverted. See, we got an OR gate here, an inverter. So with the OR gate, you have to, if A and B are both 0, you get a 1. Else, you get all zeros. So if one of my inputs are a 1, I get a 0. So it's the opposite of the OR gate. We have the exclusive OR gate. For whatever reason on this website, they have this E right here, but we generally refer to it as an XOR without this E. Just keep that in mind. Whenever you XOR, so like the symbols like ANDs are generally represented as like a multiplication in Boolean algebra. This XOR is generally represented by this circle with a plus in it. You typically don't see very many of those. This is the symbol. And an exclusive OR is like an OR, except for if both the inputs are 1, you get a 0. So it's like an OR, A or B. If they're 1, you're going to get a 1 output, but they have to be exclusive. Like A has to be exclusively 1, or B has to be exclusively. The XNOR. Here we go. Seems a little similar. It's an XOR gate, but inverted. So we have this truth table, it gets inverted. All right. And these are all your all your logic gates right here. All right, so I think I've covered enough of those. I'll move on to some Boolean identities now that we'll go over. So these Boolean identities are how we can simplify logic equations down. So first identity we have is the complement. So the complement is practically saying that whenever it's what happens when you combine an input with its inversion. So if you have an OR gate, if you have A and you OR it with its inverse, it's 1. Well, how can that be true? Well, if A is 1 and A not, it has to be 0. And so with an OR gate, as long as any of these are 1, you get a 1 as the output. That makes sense. Even if A was 0, this would get inverted and turn into a 1 and still make this true. With the AND gate, if you invert anything, if you AND anything with this inversion, you get a 0, right? Because for an AND gate to be true, both the inputs have to be 1, and this condition makes it impossible here. I had a quick question right now. What if there's more than 4 inputs for an XOR or XNOR? So remember the kind of reasoning with an XOR. So an XOR, as long as only one of the inputs are true, that means the entire equation is true. So let's say you had like a 6 input XOR gate, which I don't even know if that exists, but let's just pretend it exists. If only one of those 6 inputs were high or were true, then the entire output would be true. But if you had like 2 inputs that were true, it'd probably go to 0. But I don't really think that a 3 input XOR gate, I've never really seen that. But that's an interesting question. Moving on, the identity. So anything ORed with a 0 is A, right? Because it depends on whether A is 0 or 1. It's going to depend on the output here. Here, if you AND anything with a 1, it also still depends on A. So what this Boolean identity thing is saying is the result depends on the variable. Null elements. Anything ORed with a 1 is going to equal 1. Because with an OR, you only need 1 1 to make it true. So it's pretty self-explanatory. And kind of the inverse, if you AND anything with a 0, it has to be 0, because with an AND gate, you have to have both the inputs equal to true. So if you have one that's already equal to 0, not going to happen. So this property, interesting. So A or A is going to equal A. And if you OR something with itself, it's just itself. So this, you can remove these duplicate expressions here. And I call this like the double negative rule. So if I invert something twice, it's like I didn't invert it at all. So if I do A not, it's equal to just A. If I do A not, like 4 knots on top, it's still going to be A, because those inversions get rid of themselves if you have 2. It's like double negative equals positive, essentially. All right, gonna move on here. So DeMorgans Law. This is a important one for when we start talking about converting between NAND logic and NOR logic. So what is DeMorgans Law? So let's say I have some equation like A plus B with an inversion on top. So what DeMorgans Law says is that these expressions are equivalent. It's saying that A and B with its inputs inverted, these are equivalent expressions. And we can do something else like A, B, or like this. These are equivalent expressions. So there's a nice mnemonic I like to remember with DeMorgans Law, and it's called break the line and change the sign. So let's say, I have this AND equation right here, and I want to convert this to using ORs. How can I do that? Well, I want to apply DeMorgans Law. And what DeMorgans Law says is I can break this line on top and change the sign. So if I have a bar on top of these two elements, I can distribute this bar. I'm going to break the bar. So I'm going to have a bar over A and B. That's the break the line part, and then change the sign. That part is the sign right here. You know, it's the and sign. I can change it to an or sign. Stuff like that. What you can also do is, so DeMorgans Law, break the line and change the sign. You can also combine the line and change the sign. So let's say I started out with A naught plus B. What I can do is I can also do combine the line and change the sign. So I'm going to combine these lines, right? Like this. And then I'm going to change the sign in between them. So, right? So it's a two-way street. You can work both ways. So break the line, change the sign, and combine the line, change the sign. It's going to come in handy when we start doing conversions, when I get logic gates that I want to have, but I can't really, I'm limited to a certain number of gates, so I've got to change how I do my equation. I think we've already kind of talked about truth tables. I'm now going to talk about canonical forms. So go back to my document camera here. So canonical forms. So what do I mean about canonical forms? So a canonical form is, let's start out with the equation here. So this is going to have variables a, b, and c. And I'm going to have some equation right here. AB plus AC not. Some equation like this, right? So we see that we have this equation here, but not all of the terms, this isn't fully expanded. This is like some kind of simplified expression because I don't have 3 terms in each expression, right? If this was fully expanded, I would have, some form of A, B, and C in every term of this. So when we're talking about canonical SOP form, canonical sum of products form, that means I want to expand this equation. It's not going to be the most simple equation, right? But it's the most expanded equation. So how can we do this? I want to bring like C back into this term without like changing the equality, right? And I want to bring B back in this term. So let's go back and remember some Boolean identities, right? So we know that there's a Boolean identity that says that 1 is equal to some input, right? ORed with its inversion, right? This was a Boolean identity we talked about. And we can use this Boolean identity to get back to our canonical form, right? So let's put this in canonical form. So, right, when we have AB right here, and there's a 1 right here, right? That's a Boolean identity because we said AB ORed with a 1 is always just equal to AB itself. And so we can use this identity, right? So we can say AB, and we can say, since the C is missing here, we can say C plus C naught here. I didn't change anything with this term, right? Because this equals 1, and if I AND a 1 with AB, it just turns into an AB. I'm just trying to expand things as much as possible. And I can do the same thing with B here, right? I have AC naught, and then I can write B plus B naught here. And I can use like this distributive property of Boolean algebra here. I can distribute this term onto both these terms on the inside here. So I can write ABC plus ABC naught plus ABC naught. I get the same term there, plus AB naught C naught. And these are duplicate terms right here, right? So I don't really need these. So our expanded form of this expression is going to be A, B, C naught, like this. So this is going to be in the canonical form that we're talking about, the most expanded sum of products we have for this. So give me a minute, and we'll do one more quick example with this. I just gotta find whatever sheet I had. All right, so let's do another quick example with this canonical SOP. So let's say I have this Boolean expression. Yes, exactly. Isn't duplicate terms just combined into one? Yeah. So if you have two terms, right, that are OR together, those are just going to equal one. That's why I got rid of one of those terms. So we have A, B, C, and we have some equation, and this equation is AC plus A naught C naught plus BC. And I want to expand this into canonical form. Okay, let me look. This term is missing a B, right? So I can do AC B plus B naught here. Plus this term's also missing a B, so I can AC naught and then do the same thing, right? And then this term's missing an A, so I can do BC and then A plus A naught. All right, I'm kind of done filling out everything, so now I can do my expansion here. So I'm going to distribute these terms out. A, B, C plus A, B naught C plus A naught B, C naught plus A naught B naught C naught plus A, B, C plus A naught B, C. So I have a couple of duplicate terms here that I'm going to get rid of. So this one I can get rid of because there's another AB right there. And I don't see any final terms, so I'm going to go ahead and write this all out. So finally, this is going to be A B naught C, A naught C naught. Right, so this is our canonical, fully expanded Boolean equation here. So now we kind of understand the SOP expanded for. Now I'm going to talk about min terms. So min terms are the inputs that make the equation go to 1. So whatever makes the equation have an output of 1 here. So we have a sum of products here, right? So we see if any of these terms if any of these terms are true, it doesn't matter if this term is false and this term is true. As long as one of these terms are true, it's going to make the entire equation be true. So we refer to, if we have an SOP equation, we refer to all these, right? If you have a fully expanded canonical form, these are all min terms. So how can I go from this to writing min terms? Well, what you can do is, so you're going to assume that A is the most significant bit of the number and C is like the least significant bit. So what min term corresponds to ABC? Well, that's like 1, 1, 1, right? What number is 1, 1, 1? That's 4 plus 2 plus 1, which is 7. So this is like representing min term 7. This one's 1, 0, 1. So that corresponds, that's 4 plus 1, so this is like 5. Right? So far I have 7 and 5. This one is 0, 1, 0. That corresponds to 2. This one's like 0, 0, 0. So that corresponds to 0. We have one more here, and this is 0, 1, 1. So that's 3. So if I reorder these, I can write these as the sum of min terms. So typically it's denoted as sum, lowercase m, and I write my min terms I found here. So if you're given a Boolean expression like this that isn't fully expanded and you want to find the minterms in it, go ahead and expand it using these properties, right? You'll get to this, cancel out any duplicates, and then find out what minterm each of these correspond with. All right, so what if I want to find the max terms, the sum of max terms in this equation, right? So what the max terms are the combination of inputs that will turn the Boolean equation like to 0. And so the max terms and midterms are both unique sets. Like 0 can't be a max term in this case, right? Because it's already a midterms. So how I write the max terms, it's the sum, like this pi and a big M, and it's going to be all the numbers that aren't a midterm. So we have a three input equation, right? So the inputs are going to go, like the terms are going to go from 0 to 7, right? So my max terms are going to be everything that's not midterm. So it's going to be 1, 4, 6. I didn't miss anything. Or this. Right, and I get a total of 8. So I'm going to take a little pause, make sure everyone's okay with this one, and then I'll move on to another topic. The question, how to write the max terms from 1, 4, and 6. Are you asking about like how to write an equation that relates to those, or how I found out that those were the max terms? Okay, so you want a POS equation. So, right, you can find the max terms from POS equation. This one is a little bit more confusing. So, when we talk about POS equations, so we have SOP equations, right? So we have sum of products. And what sum of products is it's several terms that are ANDed, right? And these terms are separated by an OR, right? So we got ORs here, and these terms here are ANDed. Okay. Comparison, we have product sums, and what those are they're groups of terms that are ORed together, and these groups are separated by an AND instead. So it's kind of like a little bit of the inverse going on here. So right, let's go back to this, what I had right here. So I have some equation that says sum of max terms, and we have 1, 4, and 6, right? And I want to generate the POS equation for this. Okay, so let's think about what this is telling us here. This is telling me that if I have that the terms 1, 4, and 6, if any of these happen in my Boolean equation, I want the output to be 0, right? So let's look at this Boolean equation here. If one of these terms is a 0, right? If like say like we have like if one of these terms like ends up being a 0, right? So if A, B, and C are all 0 and this term goes to 0, that's going to force the entire Boolean equation to be 0, right? Because with ANDs, every single term ANDed together has to be equal to 1 if you want to make your output go to 1, right? So I'm now going to convert this, right? So this has 3 terms in it. It's a 1 to 4 and 6. So I'm going to have 3 different terms in my POS equation, right? And all these are ANDed together. And I'm going to have, they're going to be separated with ORs, right? This is a 3 input equation, so I'm going to have that. So I have 1, which means if if I have a 1 in my equation, I want this term to go to 0. So how am I going to do that? Well, 1 is represented by 0, 0, 1, right? So what I'm going to do is I'm going to say A, B, C naught. How did I come up with it? Well, what I thought in my mind is I want to say, okay, so if I have A is equal to 0, B is equal to 0, C is equal to 1, I want to make it to where if I write a Boolean equation, this is going to equal 0 in here. So 0 ORed with 0 ORed with the inverse of C, which is also 0, that's all going to equal 0, right? So it's like in a POS equation, this represented like 1, 1, 1, and an SOP equation, if I want to represent like 0, 0, 1, it's like the opposite. It's kind of confusing. You say A, B, and then C naught. You kind of invert them. So let's go to 4. 4 is represented by 1, 0, 0. So what I want to say is I want to say A naught, B, C. Because, right, I want this entire term to go to 0 because this is a POS equation. So if I have A naught, it's going to turn into 0, ORed with a B and a C, which are also 0. It's going to end up with 0 again. So that's good. So 6, that's represented here. And then I'm going to do kind of the same thing. A naught, B naught, and C here. So someone asks, and they must have every variable in these forms correct. Generally, yes. If you're going to write these by yourself, it makes the most sense to write out everything because you want to write these into like a canonical form where every term you have here equals one min term or one max term. So SOP, we write the min terms in the equations. POS, we write the max terms in the equations. All right. I'm going to use this to segue into another type of deal here we have is what if I want to go from SOP to POS? How do I do that? So just for kicks, right, I'm going to take this POS equation we just figured out, right? A plus B plus C and I'm going to convert this to an SOP equation. It's going to be the same thing, but I'm just converting it. So how I want to convert this? So I want to go from having ORs with groups of ands, right, to ands with groups of ors. So what I can do is I can do a clever application of DeMorgans Law with this. So the first thing I'm going to do is I'm going to put two big inversions over this. So right now I'm leveraging one of those Boolean properties I said by, if I have double inversion, it's actually the same thing as like doing nothing, right? So I didn't change the equation. Now I'm going to use DeMorgans Law to break all of this apart. So right, I'm going to break the line, one of these big lines, and distribute the line onto each of these terms here. So I'm going to break the line and change the sign, essentially. So right, I still got this line up here, and so I'm going to do A. So these insides haven't changed, but now I'm distributing what was this line right here. I'm distributing onto these three terms, and I'm changing the line. These. So I'm getting closer to what I want, but now what I want to do is I want to want to get rid of these. Like I want to turn these all into ands now. So what I can do is I can do DeMorgans Law, but on each of these terms. So I can break this big line and distribute it to all these terms now. So what I can do is use DeMorgans Law again, right? And I'm going to break the line here and change the signs in there. So I'm distributing lines here. It's going to be A naught, B naught, and C double naught now because I had already had a naught there. So it's going to turn into this plus A double naught B C. Still big here plus okay, just double making sure I'm making everything right. All right, and when you have a double inversion, you can get rid of those. So we can simplify this further too. So I have something that now looks a little bit more like POS. Now I can kind of keep on doing these tricks until I get to SOP, but for the sake of time, I'm just gonna leave it right here. I don't think we'll really have to do anything that really requires you to go from SOP to POS, but I just wanted to kind of show that. So now I'm gonna move on to using DeMorgans Law to kind of change things from like regular Boolean equations to something with ands and ors to something that's only ands, right? So let me find my example problem I have here. So I have the equation A, C, A, C on the same equation we had earlier. That's just BC. And I want to convert this to only use NAND gates. All right, let's think about this. So the first thing we should learn how to do is how to make an inverter with NANDs, right? Because I need to do a couple things here, right? I need OR gates. I need an inverter, right? Because I have inversions right here, and I also need an AND gate. So let's first figure out how to get an inverter and gates. Well, I can draw an AND right here. This is NAND, and I can draw a truth table. All right, so this is the opposite of an AND. So this is our truth table we have here. And the thing of note to see here is look what happens when A and B are the same. So if A and B are both 0, the output's 1. And if A and B are both 1, the output's 0. So what does that mean? That means that making an inverter like this is the same as tying the inputs of a NAND gate together. Yes. These are the same circuitry. These are equal to each other. That's kind of how we reason through this. So great, we know how to make an inverter. So how do we make this AND gate? Well, remember that the NAND gate is just an AND gate inverted, right? So we have a NAND gate, right? And this is just an inverted AND gate. What we can do is if we put an inverter right here, right, this works the same as an AND gate because it's like an AND gate and inversion. If you had another inverter, that's the double inversion, and it's like it never happened, right? It goes away. That's one of those Boolean identities. So what we can do is now we know how to make this inverter using NAND gates. How we make an AND using nothing but NANDs is just this. We have our NAND gate, and then we tie both of these together like this. So this is the same as an AND. All right, so we got 2 off our list checked off. So we need to find out how to make the OR gate. Now we can figure out this one with DeMorgans Law. So right, a NAND gate has this Boolean expression. It's A plus B inverted. This is what the Boolean expression of NAND gate is. And I want to change this to where I have OR gate, essentially. So what would happen if I inverted both my inputs to my NAND gate? So I put inversions over A and B, and there's a big bar across all of them. I can do that, DeMorgans Law is break the line, change the sign, but I can also combine the line and change the sign also. So what if I combine these two? I get A, I messed up here. This is an AND, right? This is not multiplication. I mean, this is not a plus sign, this is an AND. What I can do is I can combine the line and change the sign here. Sorry if I confused anyone about that, right? So this AND is going to change it to an OR, right? And these both have inverted inputs, so that goes to a line. I combine them, right? So I have this, but these cancel out, so I'm equal, I get A plus B, which is an OR, which is what I want. So in order to make an OR, what I can do with an AND gate is I can do this, right? I can have A, and I can invert it, right? Draw a bigger picture for you guys. I have an A, inverter, B, inverter, into my NAND gate, and this is the same as an OR. And like we found out before, the inverter is just an AND gate with its inputs tied together. So then I can make this all using AND gates, right? So I'm drawing my inverters. Then this NAND gate here. So this is the same as an OR. So now we can kind of put all of this together, right? So I have A and C, right? And like I said, how to make an AND, it's just an AND gate followed by this inverter right here. So what I'm going to do is I'm going to have A and C here as we're going into an AND gate. And if I invert it, we just have an AND gate, right? So that's how we make the A and C term. How about this A naught, C naught term? Well, so we're going to invert these first. Should be C. We're going to put our NAND inverter on those. And then feed that into a NAND. Then invert it again to make it behave like an AND. Alright, we got that one done. So we're going to do one more. We're going to have our B and C here. Those don't get inverted at all. Those just go straight into our NAND. This is followed by an inverter right here. Alright. So I have these 3 terms written out. This AC, this A naught, C naught, and this BC. So now I need to OR them all together. What I have to do is remember that an OR gate is a NAND gate with all its inputs inverted. So that's what I'm going to do here. So I have my 3 inputs here. I'm going to invert them first. And then feed that into my and this will give us the output F. Alright, so are we completely done? Not quite, because we can simplify the circuit a little bit more. So look at this. We have an AND gate right here that's acting like an AND gate, and then we have like an AND gate inverter and an AND gate inverter. They're both like in series with each other, and we can remember that. Yes, exactly what someone just said in chat. We can cancel these inverters, right? Because two inverters together is that double negation Boolean algebra law. So these we can cancel out, right? Cancel out these double inverters, cancel out these double inverters. So we can just, just draw a straight wire to that, right? Okay, so that's how we implement a circuit using only NAND gates. So the process to do that using NOR gates is very similar. So right, let's see, what if I need to make an AND gate out of NOR gates? So we know that a NOR gate is A or B inverted like that. Oh, what if we do the same trick we had with AND gate where we inverted both the inputs like this, applied DeMorgans Law, combine the line and change the sign, A or B, cancel that out, and we get AB. So an AND gate in NOR gates, it's like this, right? NOR gate, and we have our inputs, and they are inverted, right? And so let's say about inverters again, right? What if we want to make an inverter? Well, NOR gate, right? Truth table, A, B, F. Look at this. When A, B are the same, we get a 1, so the opposite. And when A, B the same, we get 0, which is the opposite. So an inverter with NOR gates, right, is exactly like the NAND, right? It's when we tie both the inputs together. This is the same as in. So I can do the entire process again using only NOR gates, knowing that if I invert the inputs to a NOR gate, I get ANDs, essence, and if I tie the inputs of the NOR gate together, I get the same thing as an inverter. And right, if I wanted to get the OR gate, well, a NOR gate is just an OR gate with an inverter. So if I just tie another inverter on the end, right, that double negation law, I end up with the same thing as an OR gate. So same process as we did with the NANDs. You would put all your gates on. If you got some double inverters, cross them out, and you're good to go. All right, so next I'm going to talk about our CMOS logic. So we're kind of talking at a higher level here about how we do gates like on a theoretical level using Boolean algebra. But the CMOS gates are how the gates are actually implemented using MOSFETs. So pull out this diagram here. So I have an example, some CMOS gates here. So we have our PMOS here up top because they're better able to conduct VDD. We have our NMOS here at the bottom because NMOS are better at conducting 0 right here next to ground. And so with a PMOS, it's like a switch. These MOSFETs are like a switch. So if I have a PMOS here, that's what PMOS looks like. It's like a switch, right? It's like a switch. And so whenever this input is 1, it's like the switch is it's like the switch is open, it's not closed. And whenever A goes to 0, it's like the switch closes, right? Closes like this. This is the PMOS that I'm talking about. It has this inversion symbol right here. So when A is equal to 1, it's like an open, and when A is equal to 0, it's like a close. And so the inverse is true with this is the PMOS. The inverse is true with the NMOS. So my MOS right here with the A, if A is equal to 1, it's like closed. And if A is equal to 0, it's like an open, like this. Right, so, okay. So we kind of had a crash course there. So I have this CMOS circuit right here, and I want to analyze it. What do I want to do? Okay, so I'm going to put two different types of stimuli into the circuit. I'm going to say like A is equal to 1, BC is going to be equal to 0. I want to find out what this output F is. I'm going to do another stimuli. A is equal to B is equal to 1, C is equal to 0. I want to find out what the output is. So how do I go about doing it? Well, I can kind of just test what's going to happen here, right? So let's go with case A here. What's going to happen? Well, let's look at our diagram. A is going to equal 1. So I'm going to have VDD here. Then I have this A, PMOS right here. So whenever I have a 1 into a PMOS, I'm going to have an open circuit. So right here where this A is, it's like I'm going to have an open circuit right here. This B is going to happen to it. It's equal to 0, so it's going to be like a closed circuit. So we have another branch here, C. C is also equal to 0, so it's going to act like a closed also. Down here, C is equal to 0. That's going to open that NMOS. B is equal to 0. So it's going to open that PMOS also. And A is equal to 1, so it's going to close right here. So what is F going to be? Well, since C was closed here, open, there's no way ground could get to this node. So there's no way this can be connected to this. But see here, we have a direct path to VD. So this means F is going to equal to 1 in this case. So let's do the other type of stimuli. Right. Let's say A and B is equal to 1 and C is equal to 0. What's going to happen here? So let's draw a diagram. So I'm saying A and B are both equal to 1. So if A and B are both equal to 1, right, these are PMOS, they only open on 0. So if A and B are both equal to 1, they're going to be open. So I'm going to have a big open right. About C. Well, C is equal to 0, and whenever you have a 0 in a PMOS, it's going to close the switch. So we're going to have a connection like this again. Alright, let's look at this. C is equal to 0 down here. Whenever you have a 0 and an NMOS, it acts like an open. So again, we're going to have this another open connection right here. This is going to F. Right, and then A and B are both equal to 1, so these are going to be closed right here. So we kind of have the same scenario as last time. We have this open right here, so there's no way ground can be connected to F, and we have this direct path to B. So F is equal to 1 again. Alright, so I'm going to pause right here. Make sure no one has any questions. If no one has any questions, I'm probably going to move on to K-maps now. All right, let's do K-map example. K-maps. K-maps pretty much work on the same principles. Like we can simplify Boolean equations using the identities we have, but as you know, you can make a lot of mistakes doing that. And K-map pretty much provides the same identities or way of identifying those identities and making simplifications, but they do it in a graphical way, a visual way, so you're less likely to make mistakes. So how do we draw a K-map? So let's say we have three variables, and we have just going to draw some equation here. So we have a three variable equation, f is equal to a, c. I'm going to start out with three variables, right? So let's have a, b, c plus let's think about this, a, b, c naught plus a naught, c naught. So yeah, or this one's a, c. So we have this Boolean equation here, and we want to simplify it. So let's draw a K-map for it. So I have three variables, and so I'm going to draw a K-map, and it's going to have, on one dimension, it's going to have one variable, so a here, and on one dimension, it's going to have two variables. So in this dimension, we're going to have two different cells, and on this one, we're going to have four. And I like to number the K-maps, so K-maps kind of have a weird numbering system, right? On this side, it's going to be 1 and 0. Not too crazy, right? But on this side, it's going to have 0, 0, 0, 1, 1, 1. Not 1, 0. It's 1, 1, and then 1, 0 back here. And the reason why we do this is that on adjacent cells on the K-map, I only want one change of the number. And that's going to help us do, that's how we are able to achieve these simplifications in a graphical way. So, right, so I have an equation with some min terms in it. You know, I have some terms, like this term corresponds to 1, 1, 1 here. This term corresponds to 1, 1, 0. This term corresponds to 0, 0, 0. This term corresponds to 0, 0, 1. Now, to reference what I said earlier about canonical form, if you want to do a K-map, it'd probably be in your best interest if you didn't have like a canonical SOP form to go ahead and put in canonical SOP form so you're able to look at all the midterms. So what you do is you populate all your midterms into this K-map. So right, I have the midterm 1, 1, 1, right? A, B, C are all equal to 1. So I can look on my K-map here. So A is equal to 1 here, and BC is equal to 1 here. So I'll put a 1 right here. I have a midterm right there. Go on to the next one. I said this was 1, 1, 0. So I'm going to go over to 1, and 0, another midterm right there. I have a midterm at 0, 0, 0. So this is where they're all 0, 0, 0. I have a midterm at 0, 0, 1. So I'm going to put 1 right here. All right, so I'm ready to make what's called the prime implement. So what I want to do with my K-map is I want to make the biggest grouping of minterms, the biggest grouping of ones here, but they have to be in powers of 2. So you can make groups of 1, 2, 4, 8, etc., right? You want to make the biggest group. So the rules are you can't make groups diagonally. So if I have like a 1 here, I couldn't do like this, right? That wouldn't make sense. I can only do them like horizontally. Now these, I can, if I had all 1s here, I could circle all of them. And if you had some 1s that were on this side, I can also wrap around the sides, up and down on this K-map. So let me find the biggest groups I can make, you know? So I have two close together here. I don't have any others on the side or anything else that can wrap around. So this is going to be our biggest group here. And the same thing with this one. This is the biggest group here also. All right, so I've circled my prime implicants. What's the next step? Well, how do I come up with what expression those prime implicants create? So I'm going to look at A, B, and C. So I'm going to look about how these numbers are changing, and I'm going to write down the numbers that don't change with this circled prime implicant. So let's look at A. Well, for this prime implicant, look at this. A doesn't change throughout this prime implicant. So we know that A is going to be like 0, right? So I'm going to write A naught. Let's look at this BC term. So from here to here, we go from 0, 0 to 0, 1. What's the term that's changing? Well, it's C. So C is the term that's going to be factored out here, and B remains 0. So it's going to be B naught. All right, we just came up with the SOP term that corresponds to this prime implicant. So I'm going to write a plus here and move on to the next one. So let's look at this one. Let's look at A. A doesn't change throughout this entire prime implicant, and A is equal to 1. So I'm going to write down A. Let's look at the change in BC. What doesn't change and what does change? So from here to here, it looks like B stays the same. B stays 1, but C changes from 1 to 0. So C is going to be the one that gets factored out. So we're going to be left with B, right? Because B doesn't change. It always stays a 1. So this is our function f now. And this has been simplified. So we have AB and A naught, B naught. So that's how we do a very simple simplification using K-maps. We can create up to a 4 variable K-map. Those are the biggest types of K-maps you can create and kind of be able to get through it visually. You wouldn't want to create any K-maps bigger than that. They get pretty messy. Just to, as an example, let me bring up a 4 variable K-map here. So I believe these are one of your challenge questions slides. So let's say we have this Boolean expression, right, that we start out with, and we see they were very nice and give it to you in canonical form. See, each term has all 4 variables in it. So each of these terms corresponds to a min term, which is nice. So this min term is 0, 0, 0, 0, right? So I'd create a K-map and number it. So we have WX on this side. I like to put the most significant bits on this side, the least significant bits on this side. And it kind of has that funky numbering system. You need to make sure you get it right. It goes from 0, 1, 3, 2. 0, 1, 2, 3. It's 0, 1, 3, 2. Be sure you do that. Same thing on this side. And so, right, we have all our minterms here. This is in canonical form already. So what are we going to do? We're going to populate the minterms, right? So this is all zeros, right? So 0, 0, 0, 0 is right here. We're going to put a 1 right there. What's the next one? This is 0, 0, 1, 0. So I'm going to find 0, 0, 1, 0, right? This corresponds to this midterm. I'm going to put a 1 there. Next one. So I'm going to keep on doing this, right? And so we get all of these populated here. And you're going to circle your prime implicants. Now, you probably see this very funky circling right here. It's kind of tricky. You have to remember that this cell is actually connected to this cell. You can wrap around. It like wraps around here. The same thing with this corner also. This corner wraps around over here. So like all these corners have a 1 in them. And all these corners are connected because this corner is connected to this corner is connected to this corner, corner is connected to this corner, and this corner is also connected to this corner because you have all these wraparounds. So we're able to circle all 4 of these, right, into one prime implicant, right? Instead of making a prime implicant with 2, we're able to go up to the next power of 2, get up to 4. These, if this one was set to a 1, we could circle all 4, but we can't. So we're forced just to make 2 separate prime ingredients with 2 each, right? And so we'll go through the same process where you look at which ones are the same, which ones are different, and write down your equation, right? So let's look at this vertical prime implicate here. We see, so it goes this, right? So Wx is going from 0, 1 to 1, 1. What is changing and what's not changing? Well, W changes from 0 to 1. So that's the term that's going to be like factored out essentially. So we're left with X. So X is going to equal 1. So we're just going to write X in our equation. So this is what this X is right here. Let's look at the YZ, right? YZ stays the same, right? YZ doesn't change, right? We're not going across like this, we're going like this. So YZ is always 0, 1. So we're going to keep those. So Y, so we're going to have Y naught and Z. So that's where we get W, Y naught, and Z. That's where that term comes from. All right, that was my kind of basic overview of the K-maps. Going to stop for any questions. If there are no more questions, going to briefly cover some of the more bigger combinational logics. So adders, subtractors, muxes, inverters, that type of stuff. And then after I kind of briefly go through that, I'll open the floor to some questions if you guys have some particular questions you want worked out. All right, I'm gonna just go through real quick. So we have multiplexers, right? Right, the multiplexer is kind of like a big switchboard. So we have some kind of selector here. Those are the selectors at this bottom of the mux, and then we have our individual lanes we can take. So each of these lanes corresponds to a certain position on this control lever. So typically you see muxes drawn like a box like this with selectors. And another way you'll see muxes drawn is like this. You'll see a mux typically drawn like this. You'll have a trapezoid looking deal, and you'll have control lines right here. Right, so this is like a 2 to 1. I drew this wrong. Got like 2 lines coming in here and 1. Then we have a select, and this is like our AB, and this is our F. So this is called a 2 to 1 mux. So what does the truth table of this look like? So you have A, or let's actually draw this like this as a function of S. So S is only 1 bit, right? I only have 1 S, so there's only 1 or 2 possible combinations. So let's say S is 0. What's going to happen? Well, going to end up like this. Whenever S is equal to 0, it's like, so we have like a switchboard in here, right? So whenever S is equal to 0, it's like we have a choice between A and B here, and this S tells us which one to pick. So if we have an S equals 0, it's like, oh, I'm going to select A here, move my switch over like this. And when S is equal to 1, it's like I'm moving the switch over to here. Right? So that's how that works. And you can have bigger types of muxes, right? So like you can have a 4 to 1 mux, right? So a bigger multiplexer. So we have F right here, and we have A, B, C, E. And what does that truth table look like? Since we have 4 bits right here, we need S1 and S0 to represent our selector, right? So now our truth table is going to look like this: S1, S0, and F. 0, 0, 1, 1, 0, 1, 1. So we're going to have A, B, C, D. So it's like a four-way selector here. We can select that one, that one, that one, this one. And what connection is made internally depends on these S inputs right here. And that's kind of what these slides are saying right here, right? Because whenever the selector is equal to 0, it's like selecting this I0 right here, and so we see that I0 is being reflected into Y here. So when the selector is set to 1, it's like I'm making the combination, the connection between I1 and Y. So we see I1 is reflected in the output. So a priority encoder is like, so we have like the encoders. So an encoder is like the opposite of a mux, essentially. So like a mux selects one of multiple inputs. It's like a train track switch, like that analogy we made. Encoder like converts individual inputs to some kind of binary. So let me just briefly talk about an encoder real quick. Before I talk about the encoders, the adders are just it's just the combinational logic way of being able to facilitate like that addition we were doing earlier. So every digit we add, we have a full adder to facilitate it. So these will add all the bits together. And a ripple carry adder is so we have every time you add like a singular binary digit, right, you could have a carry, right? If we add 1 and 1 together in one cell, the result will be 0 and we'll have a 1 that carries over. This allows that carryover to be included in the next, set of calculations, right? So if you have a carry, it's going to be able to add that carry when it goes to the next digit. Briefly talk about encoders, and then I'll open it up to questions. So, encoders. So very briefly, so we have the mux, right? It goes 4 to 1. You go from a lot of inputs to a few outputs. So let's talk about our encoder. So encoder is like the opposite. I have like so let me draw like a let me look at my notes. Just make sure I'm telling you guys direction. So let's do like this encoder right here. So like this represents like a 1, a 0, a 1, a 2, and a 3. This is like your S output. So let's draw a truth table. So let's say A is 1 and everything else is 0. This is practically representing, or this is S. This should be like S1 and S0, right? So this is like the zeroth selector, and whenever we have an A is 1, that's going to be like telling the output to go to 0, 0, right? If we have B selected, B is like this number 1 here, so this output's going to go to 1. We have C here, this is like 2. So if C is 1 and everything else is 0, this is going to go to 2. And if we have a D that's equal to, if we have D is equal to 1, everything else is 0, I have this, right? It's going to go to 3. So this is all fine, but what happens when like A and B are both set? What's going to happen? Well, this encoder doesn't really like that. So what we can do is let's make, this is the priority encoder. So what we have here is we have the same type of thing, and we have this valid bit right here, right? That tells us whenever the output's valid. So let's look at this first case in the truth table. Everything's set to 0. Well, I don't really have a valid input, right? One of these needs to be set to 0. I mean, set to 1. So this V is going to say 0. I don't have a valid input, and X and Y are don't cares. They're like, you didn't really give us an input, so we're not really giving you an output. So with this encoder, A has the highest priority and D has the lowest priority. Let's look at D. So, and this is like 0 to this case. So when D is set to 1 and everything else is 0, X, Y, they're going to say 0 pretty much, and this valid bit goes to 1. Whenever C is 1, it doesn't even matter that D was set to anything. C has priority over D. So it doesn't matter what D is, this output's going to 1, and the valid bit gets set to 1. Same thing with B. What if B is set? Well, B now has the highest priority. Right, this is ascending priority. So what's going to happen is, if B is set, the output's going to reflect what B is, which is 2. So it's going to say 2. And in any case, if A is set to 1, A has the highest priority over anything. It doesn't matter if B and C and D are all set. A has the highest priority, so anytime A is set, it has priority. It doesn't matter what B, C, or D are doing. The output's going to 3, which is the A's associated count, and the value goes to 1. Okay, that kind of concludes what I wanted to go over today. Hopefully we didn't have too many technical difficulties. I know the camera's a little out of focus, but hopefully if we have another review, I'll have that a little bit better equipment. So I'm going to open it up to some questions. So if you guys have some questions for me, go ahead and type that in the chat. I'll wait here a little bit. If you have a particular question that's not really well reflected in a YouTube chat, you can send me an email here. Type it out in the chat, and I'll be around to answer your questions until 9:30 or so. So if you have a question, you can send me an email, and I'll try to get back to you with a response, maybe. But I'm not going to really answer beyond 12 because that's when your guys' test is going to begin. So, yeah, so if you have no further questions, you can feel free to leave, and those who have questions can feel free to stay here or type in the chat if they want another particular set of problems solved. So Mark said, why are there 3 outputs instead of 2 on this encoder. So this is the priority encoder. So, right, it's like kind of like a normal encoder, right? We have 4 inputs, 2 bits, right? Because this represents 0 to 3. So in order to represent 0 to 3, right, you need 2 bits, right? So that's why we have this XY here. This V is put there. This is what you guys had in your textbook. This is just a valid line. This tells you whenever your inputs right here are valid. So what it's practically saying is if A, B, C, D are all 0, that's not a valid input, and I don't really care about that one. But if I have, a 1 here, that means my output's valid, and that means XY is valid. So V is kind of like a status bit in this particular example. I do remember one thing I wanted to talk about. I wanted to talk about overflow conditions. So I'm going to wait here for about 2 more minutes. If I don't have another question, I'm going to talk very briefly about how we can, what an overflow means and how we can detect overflows. All right, so I'm going to talk about overflows real quick. I almost forgot to talk about that. I might run out of paper. There we go. Some black paper here. So what is an overflow? So a lot of times we're dealing with a fixed number of bits, right? Like my computer is like an 8-bit computer, so I'm limited to 8 bits to represent my number, right? So, an 8-bit number, if it's unsigned, let's talk about unsigned numbers here. We're not talking about 2's complement. Let's talk about an unsigned number. I know that 8 bits, right, can represent 2 to the 8 numbers, right? So 2 to the 8 unique numbers. And so what is that? 2 to the 8 is 256. So I can represent a number I can represent 256 numbers, and the highest number I can represent is 2 to the n minus 1. So that's 2 to the 8 minus 1, which is 255. So with 8 bits, the highest number I could possibly represent is 255. So an overflow is what happens when we try to do some kind of mathematical operation and we don't have enough bits to represent it. So what happens? So be very careful about this. I'm talking about unsigned numbers here. So let's say I want to add 100 plus 200. You can already probably see this is going to be a problem, right? Because 100 plus 200 is 300, and that's greater than 255, which is bad, right? So let's see what's going to happen here. So 100 in binary is this, plus 200 in binary is this, if we have 8 bits available. Right, and I'm going to add them like we did earlier. So 0 plus 0, 0, 0, 0, 1 plus 0, 1, 0 plus 1, 1, 0 plus 0, 0, 1. This is a little bit different. Here we have a 1 plus 1. 1 plus 1 is 0, right? And then we have a carry bit that's going to go over here. So we have this, 1 plus 0 plus 1, that's 0, and then we have a carry bit right here. All right, look at this. We have a carry bit in this digit right here. We already have 8 bits right here, and we can't have 9 bits, right? So this bit gets thrown away, right? This is going to trash. So our final answer is this that's boxed right here. Well, what number is this? So this is 2 to the 5th right here. That's 32 plus 8 plus 4, right? Which is 44. But wait, my answer is supposed to be 300. That doesn't make sense. So what happened here? Well, what happened is that we don't have enough bits to represent the number 300, so we got truncated. This carry bit, we couldn't include it. So when we're working with unsigned numbers, if you want to detect an overflow, detect if you have a carry in the most significant bit. That's how you detect an overflow with unsigned numbers. I'm stressing this. This is only unsigned numbers. So, all right. So let's say we're working with two's complement math. So right, it's a little bit different because we can represent signed numbers now. So now we can have a range. It goes from 127 to negative 128. And I might have this backwards. It might be 128 to negative 127. But, you know, I have the same dynamic range, but now I can include negative numbers. So these are the rules that you want to follow. So with two's complement numbers, how should we detect an overflow? Well, we don't want to look at this carry bit because the number system is a little bit different, right? Because the most significant bits typically represent signs, and if a sign overflows, it might not matter in a lot of cases. So these are the two things. These are the things you want to keep in mind. So if you add two numbers, so add two numbers with different signs, overflow is impossible. There's no way your number can overflow. So what do I mean with by numbers with two different signs? So if I have a two's complement number, let's say I'm adding this two's complement number to this two's complement. Remember what I said earlier in this review section? In order to find the sign of a two's complement number, you look at the most significant bit here. These signs are opposite. It's like you're adding a negative number to a positive number. And since some portion of them are going to cancel out, there's no way we can get overflow. There's no way we can get a number that's too big or small to be represented using our current number system. So what's the second rule? So if we add two numbers with the same sign, if the result has a different sign, that's when the overflow occurs. And that makes sense, right? Let's say we're adding two positive numbers together and we come up with, so we add two's complement numbers together. So the most significant bit of those two numbers is 0, and the result we get has a 1 in the most significant bit. So we added two positive numbers, and the number we got, which has a 1 in the most significant bit, that means it's negative. And there's no way we could add two positive numbers and get a negative number, right? It's just not possible. If I add 100 and 200 together and I get negative 47, something went horribly wrong. So that's how you detect the overflow in two's complement, right? So there's two different cases. If you add two numbers with different signs, there's no way you could overflow. But if you add two numbers with the same sign, if the result has a different sign than those two numbers, an overflow occurred. That's how you check. All right, just wanted to add that out there because there might there might be something about detecting overflow. So, all right. So, like I said, I'll be here in chat for another 15 minutes or so. That's really the end of all I have to say now. So, stick around if you have some questions, and if not, have a good night, some rest, and wish you luck on the test tomorrow. All right, guys. Haven't seen any more questions, so I'm gonna sign off here. So you guys have a good test tomorrow. All right.